Alright, I'm going to continue on with the design. I have put a little bit of extra graphics on this schematic after copying the second driver in here, and after changing all the labels that will go to the CPU to say number 2 there. And in this video I will add the bulk capacitance. The main purpose of the bulk capacitance is to absorb energy from the motor as the speed of the motor decreases primarily, and also to supply the motor with more energy if there is a sudden request to increase the speed of the motor. So it's very important to have sufficiently large bulk capacitors to both protect the electronics a little bit and to provide this extra current surge from these capacitors to the motor. The data sheet of this chip suggests to use 220 microfarad bulk capacitors. There's a special section that specifically deals with the bulk capacitors and the choice of the bulk capacitors. So I'm going to try to find this section. Let's see, bulk capacitors. Bulk capacitance. So in terms of size, I don't want these capacitors to be higher than around 15 millimeters. So I don't want the capacitors to increase the size of the enclosing case of this motor drive. Right, the highest current required by the motor, the capacitance of the power supply, ability to sink current, amount of parasitic inductance. Right. Right. Exactly. So the voltage rating that I will use for the bulk capacitors will be 63 volts, and because the motor drive chip has the maximum operating voltage of 60 volts, I have to drive the motors with something that is much lower than that, because there will be a voltage rise on the power lines. And before the circuit is able to respond by, for example, engaging the brake resistor, there needs to be a sufficient margin to protect the motor drive. But also, I will have extra protection that will clamp that voltage at 60 volts maximum. The operating voltage will be 48 volts, and the capacitors I'll choose will have to be at most 15 millimeters high. I think I'll go with the recommended value to begin with, and I'll see if I can find any capacitors that are of sufficiently small size and that have a capacitance of 220 microfarads. Let's remove both of these filters, and I can remove, or in fact, let's go to capacitors and configure the filters from the beginning. I need a capacitor of 220 microfarads, and I need the voltage of this capacitor to be above 63 volts. Above or equal to 63 volts. So we can apply the filter and also choose components that are in stock and that are compatible with ROHS directives. So maximum length, let's see if I can specify vertical mount. let's specify maximum height. So anything that's less than 15. Okay, so we have 10 alternatives. And I suppose that anything that has a height specified is going to be a standing capacitor. And I also think I will use a part that is a through-hole part. It's going to be easier to solder. It's going to be a better solder joint as well. Let's see. And there's going to be less chance that the capacitors will be knocked from the board if the board falls or if there is any kind of stress exerted on the board. But I'll choose the capacitors that are a little bit more widely available. And yet the fact that the through-hole parts are not as widely available with this size almost makes me want to go with surface-mounted capacitors anyway. If I'll choose a through-hole part, it's going to be this one, I think. So 63 volts, and we have 220. So there is apparently no capacitor specified at 220, at least not at 63 volts. There is one that is specified at 80 volts. So could this be something higher? This is 80 volts or 100 volts. Okay. The one that is 63 volts is a different capacitor. What is the height of this capacitor? 20 millimeters is the length. So the length is actually 20 millimeters. I suppose that they have a little bit of a messed up data in this database, where the length is actually the length of the capacitor, while the height is the diameter. So searching for the length or the height will not give all of the results. So I'll remove that, and now I have a little bit larger number of parts to choose from, and I can look at, let's see, so yeah, the voltage needs to be set to 63 volts. Let's pick 63 volts actually. No. Damn it, that's the wrong value. It has to be the DC voltage. I have to pick the DC voltage. So loading page, and now I can pick the DC voltage, and I'll set it to exactly 63 volts because I don't want to see any parts that are above that. They're going to be oversized, most probably. And the height of this part, I'm just going to sort it by price first. And then I'll look at both height and length. So I have 15 millimeters and 10 millimeters diameter. And the price is not in this pane, come on. I want to see the price, I'm not interested in the manufacturer. Okay, I want to see the price and how many they have in stock. I think this one looks good. Although it's 20 millimeters, it's a little bit higher. 4,000 in stock. I'm gonna go back to the beginning here and check these ones. There is 10 times 16. Let's have a look at the first 15 millimeter capacitor. That would be this one. $2,000 in stock. I think I'll go with this one. For now, this one will work, and I can switch it out later for something either maybe a little bit longer or a little bit shorter. But in terms of diameter, most of these caps are 1 centimeter. See if there's anything that's different from 10 millimeters. They're all 10 millimeters. Okay, so I'll use this capacitor as the part for the bulk capacitors. I'll add the part first. So this would be a cap P, which is a polarized part with the polarity, and then this would be 220 microfarads and 63 volts. And it would be 10 times 15 THT. I'll hide this, be deleted, and I'll hide this one. This one is not supposed to be shown. And I'll change the label to 220 microfarads, 63 volts. Very good. And the footprint for this part will be a through-hole capacitor of 1 centimeter in diameter. Is there, let's see, okay, so this is radial. Diameter 10 and pitch, okay, yeah. So I need to check the datasheet for the pitch of this capacitor. I think it was, must have been this one, yes. So let's see what the pitch is. Maybe it actually says on the product page what the pitch is. 5 millimeters. So we can go with this one. This is the capacitor. This is the footprint for this part. So we'll go back and I'll run my script. My script updates the fields, and then I can add the part to the schematic. I'll add 6 of them, even though the reference schematic has only 2. I'll add 6 of them and I'll place them by the MOSFETs. So they'll align in one row by each driver. And then let's see what else there is here. Let's see. There we go. And they use a few smaller bypass capacitors. I think we can put the bypass capacitors close by as well. Although they're not strictly necessary in this case. Let's see, 100 nanofarads would be placed here. And I'm just going to check the layout. We have a recommended layout here somewhere. Let's see how they place the capacitors. So they place the bulk capacitors on each side of this driver. And they have the PVDD coming in on an internal layer. Okay, right, so they use the 2.2 microfarad capacitors by each MOSFET there, and then they have the larger capacitors on each side. So that explains why they only use 2 of them. And where do they put the smaller ones? So okay. So 4.7 and 0.1, that's for the chip. So that doesn't actually even belong here. Let's see. Cut this. And I'll actually remove this as well. So I'll just have 4 capacitors. 2 of them on this schematic. And let's see. Let's actually place them right there. And then we have the other 2 on the schematic here. Now I'm pretty happy with this structure of the bulk capacitor circuit. And I'll just double check whether 4.7, where was that placed? 4.7 microfarads. Where did we put it? Okay, so 0.1. Okay, right. So they actually have another capacitor there, another pair of capacitors, which I have as well, I think. Yes, I do. But then they have this capacitor, 0.01 and 0.1, and I'm curious where they actually placed it on layout, which would tell me the purpose of this of these two capacitors. And then they have, okay, so PVDD2 should also have that. So let's see, PVDD1, PVDD2. Okay, right. So PVDD2 is actually for the buck converter, so I don't need to worry about that. It doesn't drive anything else on this inside this chip. So I don't need to worry about PVDD2, but what is the purpose of the two capacitors that are placed by the MOSFETs? So we have the buck converter and we have is that a 1 ohm resistor? Interesting. So that resistor does seem to be 1 ohm. And what do we have on the schematic then? Did I put wrong resistor in that connection? Okay. Right, it's 1 mega ohm there, but it's 1 ohm there. So obviously using 1 mega ohm resistor is not correct. But why do they use 1 ohm and not just 0? Let me check the description here. Strong resistor. Right, so it can be 0. Right. So why use 1 ohm? Absolutely unnecessary. This one just goes to ground. I suppose I'm not gonna be experimenting with the dead time, because so putting if I put a 0R resistor there, I could actually adjust the dead time later. But I think it's completely unnecessary, because I'm gonna be using the dead time generator inside the STM32. So I'll just wire that to ground. I'm gonna do the same thing here. Okay. But I still don't know where these two capacitors are, and the resistor 3.3 ohm. What if I search for? Can I search for this text? How do I make an omega sign? Let's see. 3.3. Is this gonna even find 3.3? Yeah. So maybe this is gonna find the 3.3 ohm resistor. No, it didn't. Okay, going back here and going back to going back here. Maybe this is a picture. No, it actually has text there, but it's not on this layout. I cannot see any resistor here that's connected also to a capacitor. Besides that, but that's for the buck converter. So no idea really. I have no idea where they put that that little capacitor there, and the capacitor and the resistor. Maybe they put it there to somehow filter the PVDD sensing signal, but there doesn't seem to be any point in doing that when we have a capacitor after the 34 kilo ohm resistor. This capacitor is not going to do anything, at least not for any noise that's going to appear here. Okay. So the PVDD line is going to be very noisy. It's going to have all kinds of switching noise and disturbances that have to be filtered out, and they're filtered out here by this capacitor. It's possible even to make this capacitor a little bit higher capacitance eventually. But the downside of that is then that we won't be able to sense a quick increase in the PVDD, such as, for example, when the motor is stopping. So there is a trade-off for making this capacitor larger. So for my schematic, I'll use the same circuit, but I'll use resistors that have a different division between the two resistors in this bridge, because I'm running from 48 volts, not 24 volts, as they do in this schematic. So let's see. I can add the PVDD sensing circuit like this. This is just too much work. I'll just do like this. And then also I can put the diode. And even though in this case it's the lower side diode is never going to be used, I'm still going to be using the same part, just to keep the BOM size down and just not having to add an extra part to the library just for this. Just for the purpose of clamping the voltage on this voltage sensing pin. So this will be vmod sense, and this will go to vmod, and this one will just connect to the bridge here. This will be VDD 3v3, 3v3 ref actually. The problem is that this can actually be a problem because we don't want to inject any noise into VDD 3v3 or the VDD 3v3 ref. and we may inevitably inject some noise into this supply if the voltage here exceeds the supply voltage. Although we should never do that anyway. That would be kind of a error condition. Because of that, I'm going to leave it like this for now. I'm going to leave it connected to VDD323ref, and I'll have a think about it, but I think this should be fine. I think this should be very good protection of the voltage sensing inputs. Now, actually, let's make this 3 to 3. There is no reason to not make this 3 to 3, because this is just used for clamping, and we don't want to inject any noise, as I said, to the 3 to 3 ref. And I think I just put the wrong label there, because I used 3 to 3 here, and 3 to 3 makes perfect sense here. I'm going to use the 3 to 3 ref very sparingly, and I'll use it just for the reference voltages. Anything that's connected to the 3 to 3 ref is never going to inject any current into that power line. Yeah. Now I feel happy about this. I think this is good. Okay. So bulk capacitors are added, and the motor supply voltage sensing circuit is added. So I'll stop this video, and I'll continue with the design of the schematic in the next video. Thanks for watching, and subscribe to my channel for more electronics design videos. Thank you.